So as we left off here, we do want to identify a solid from a net. So what shape does it do? And also, how do the sides / faces interact with each other? In a three-dimensional object, just to be clear, in a three-dimensional object, each of these, what are squares, each one of these is called a face. We'll cover that more when we cover solids, but that's called a face. We tend to say, oh, that's the side. But actually, in this case, each of the black lines, which are right now are black, all the black lines, those are sides. Each of these, that's a side. So I'll try to use face is dealing with the polygon on a three-dimensional shape, and a side is a one-dimensional shape on the edge of a two-dimensional shape. Okay, so four of the five other letters will touch some side of face B when the net is folded into a cube. Cross out the letter of the side that will not touch. So if we look at this, notice when something doesn't touch, there's a couple different explanations for it, but one of them is that the two faces are going to be parallel, that they're not going to touch. So if we look, here is B, there is B. So the question is, what's on the back side there, that we can't see back there? So what letter is that one? Good, so D is correct because that's going to fold back and be immediately behind D, not touching. So notice that there is a gap between the two. There is this gap right here between B and D. So it's not touching, the polygons aren't touching, therefore the faces aren't touching as well. All right, continuing on here, so that would be my D here. Cross out the letter. Which of the cube will that letter be on? So which side? Is it going to be top, bottom, right, left, or back in class? Where is D going to be?
Back.
So indeed it does go to the back. All right, which face, using the net, which face is to the right of face B, and how do you know? Good, so just looking right here, we see that going around the corner here, that's to the right of B. So going around the corner, since the B's here are physically oriented the same, then we can follow that. So C is going to be to the right. And how do we know? C, and it has to do with it being adjacent. Has to be that it's adjacent and to the right. Good. All right, so use the net. Which face is on the top of the cube, and how do we know? All right, and what'd you get back there? Good, so which face is on top, and E would be the answer there. And notice here that it is opposite, so the E and the F don't touch over here. The E and the F don't touch, so that means they're, in this case, on opposite sides. So before we get to the nets, let's take a gander here. 3 of these faces are going to be rectangles. Is that true or false? Well, hard to check or hard to see if you just jump to it. I saw a lot of people instantly jumping to triangles. But if we look at this guy, that's a rectangle right there, here. Then there's a rectangle down underneath. And on the left side, that guy's a rectangle as well. So the answer to that question is true. There are 3 rectangles. In fact, something you can say about 2 of the triangles. In a moment, we'll get to that. 4 of the faces are triangles. That's false, as we see only the front of the tent and the back of the tent are. And the figure has 5 total. Good. So let's look at some different types of nets. So one net that was drawn looks like this here. All right, so here we do have it. I'm going to start labeling the 10. Notice I have a 10. I can write the 10 right here as well, which describes this side right there. The 4 here, and I can also put a 7 in. I could put a whole bunch of more information, but I don't need to because it's kind of implied in the diagram right now that this side here is the same size as this one there. Yes? Mathematicians always ask ourselves, is there a faster way to do something, an easier way? And the answer is yes. Notice you can do this little tick mark here, which means they're the exact same size. So that means these guys are all the exact same size. They're all 10. So how do you differentiate if you want to say it's a different size, but also the same size, and would maybe make smaller ticks? So this guy is congruent to that guy, so I'll put a double on that, and then triple there and triple there. So that does cover everything. Not required, that's more than you needed, because all we wanted to do was a quick 4, 7, and 10 down, but that's sufficient. We write a description of this. There are multiple ways to write descriptions, and depending on what your goal is, they'll be sufficient. Now, one way to describe this is simply to say that I have three rectangles and 2 triangles. And I'm going to abbreviate triangles just by drawing a quick triangle with an S. And that is a very fast way. Instead of writing triangle, use that symbol instead. Okay, you could simply say that. You could also go on to say that not only are these triangles the same, 2 triangles, but 2 triangles that are congruent. And congruent is a special term here. We haven't described it yet. Oh. Congruent means the same shape and the same size. We'll unpack that later. But there's a great thing to say. These are congruent. And it turns out that 2 of the rectangles are congruent. If you wanted to be more descriptive. But had you just simply stopped right here and said, it's 3 triangles and, 3 triangles and 2 rectangles, that's sufficient. Good, so as we look at these puppies, this guy here is going to give me a pyramid. A pyramid. Now this one, of course, is the accurate diagram right there. And this one over here will also give me a pyramid. Did you know that? Yes. It just happens to be that the base of the pyramid is the same as the other ones. So this puppy here will also give me... All right. Next. 2 other types of drawings that we're going to look at. So number 1, we did net. Number 2, please impress your friends by using this word. Hello, we're going to do an isometric drawing. Iso means same, and metric means measure, and I have no clue why it's done like that. My guess is that each of these forms like an equilateral triangle, so all the distances through here are the same. Okay? That's my guess if I had to break it apart. Although I could be wrong about that. I've been wrong about a few things in life. Okay, the cube structure has how many edges? So first we have to define what an edge and a vertex are. So edges and vertices. Okay, so number 1, the edges are the lines, or more specifically, the line segments. The line segments. Okay? What it takes to draw the shape. Now, just to give you a heads up, this is the plural, is vertices. English being a stupid language, the singular is vertex. So when you think vertex, think corner. Not coroner, where dead people go, but corner, where you go if you're bad. All right, so if we were to go over to here and count the vertices would be any of these corners. I see a few there, I see some there, and I see some here, and we're going to have to probably make an exception momentarily. Yes. So we must take into account the ones in the back as well. But how many are those? Well, there is one. Notice that according to this diagram, the implication of this diagram is that this goes all the way back to something back there, and it goes this way here. So it's not like there's an extra cube back there, and so it looks like there's only one vertex back there. Looks like there's only one vertex back there. If I were to rotate it around, you would see something like this. Right? So if I just look at it from the side, that's what you would see. And that would be the only vertex you can't see. Because this is all straight, so all in the back there is straight. This guy here corresponds to this there, and then there's a matching one there. So, all right, so it looks like there's only one more vertex hanging out in the back. So let me catch that. Try that again. Let me count that up again. So it looks like there are 17 vertices. So hooked on phonics works for me. So the ones that you can see would be 16. Thank you very much. Sometimes